Hey, what's up, guys? Today we're going to continue our probability discussion. We're going to be talking about something called conditional probability. And what conditional probability is, it's just the probability of an event occurring given that another event has already occurred. All right. So it basically means what are the chances of something happens if I already know that something else has happened? All right. And we have a special notation for this. And it's the probability. We call it the probability of A given B. All right. So that means B already happened. So what's the probability of getting A? All right. So let's look at some examples. And some of you may not be that familiar with decks of cards, but we're looking at you have a deck of cards and select two cards in sequence. What's the probability that the second card is a queen, given that the first card is a king? So if you don't know cards that well, there are 52 cards in a deck. All right, there's 4 of each type of card, 13 of each suit. So when I say each type of card, that means twos, threes, kings, queens, jacks, aces, etc. When I say suits, each suit is hearts, diamonds, clubs, and spades. All right. So we're saying what's the probability that the second card is a queen given that the first card is a king? So what that means is if there's 52 cards in a deck, given the first card is a king. Now we are going to say that that king is not put back in the deck. So if there were 52 cards before, now there's 51 cards. All right. So that's going to be our denominator. Don't know why this is getting put all the way here. And how many queens are there? Well, there's still 4 in the deck. So the probability of getting a queen given we already got a king equals 4 out of 51. All right, so that's conditional. That's an example of conditional probability using playing cards. So we already know something happened. What's the probability of this other thing happening given that we already know? All right, let's look at this example here. All right, now this is the results of a study that basically researchers were looking at children's IQs and the presence of a specific gene in that child. All right, so let's look here. And we got a table here. So we have a high IQ, normal IQ kids, and the total. We have was the gene present or was it not present, and the total. All right. So the probability of not having the gene. Well, if we look at this column right here, there are 30 that do not have the gene. And there's 102 total. So the probability that one of these children does not have the gene is 30 out of 102. We could convert that to a decimal, but I'm not going to do that right now. I'm sure you know how to do that. All right. Now, let's try a little bit harder with our conditional probability. The probability of not having the gene given the child has a normal IQ. So Given the child has a normal IQ means that all we're going to be worrying about is these kids that have the normal IQ. So how many kids have a normal IQ? 50. That's going to be our denominator. And then not having the gene, given they have a normal IQ, that's this 11. Okay? So we go 11 out of 50. And that one I can do in my head. That'd be 0.22 of a probability. All right, I hope that made sense. Since it's given we have the normal IQ, we're only worrying about the normal IQ people. Not me and you guys, of course, we're in the high IQ range. All right, part C is the probability of having a normal IQ given that you have the gene. So now we're only worrying about these. It's given that we have the gene, so the gene is present. So we're only worrying about these 72 people. So our denominator is going to be 72. And normal IQ is these 39 out of those 72. All right. So there are some examples of conditional probability. One more term I just want to throw at you is a concept of independence. And two events are independent. I don't want the R bolded, my bad. If the occurrence I can't spell. If the occurrence, one, C, two R's. That's not there. It's a word, trust me. Of one of the events does not affect the probability of the other one occurring. So if we want to use notation, we could say two events are independent if probability of B given A equals the probability of B. So that given A part doesn't actually affect the probability at all. And if we were talking about the cards, the given A wouldn't really matter if we were to have, after we picked the king, we shuffled it back in the deck again. All right, so there'd still be 52 cards. There'd still be 4 queens. So that would make those two events that were originally not independent, now they would be independent. All right, works the other way, of course, or the probability of A given B equals probability of A. All right, notation, understand it more conceptually than the notation. If two events are not independent, they are unsurprisingly called dependent. All right, it's going to be a pretty short assignment this time. I'm going to take it from the book because I really like the way the book does these next couple sections. So I'm just going to take a picture of the page and tell you which problems to do. After we get into the next unit, we'll get a little more detailed So you'll have more problems. The next assignment, this one should only take you 5 minutes or so. But as always, if you need help, just ask. All right. Have a wonderful weekend. Peace out.